Hi, I'm Taeyoung Park from Sungkyunkwan University. Today I'll present our paper, Lockify Understanding Linux Distributed Lock Management Overheads in Shared Storage. Before presentation, according to the co-chairs, there is only one short paper accepted this year. So I think we can recalculate the accept rate is 5.6%, and this is that 5-6% presentation. Thank you. Just ice-breaking. So back to the presentation. In these days, storage disaggregation in data centers becomes common through the technologies like NVMe over fabrics. But not only just accessing remote storage, if you want multiple nodes to access concurrently, then we need a specialized file system named shared disk file system. And we'll focus on the Linux shared disk file system named GFS2 and OCFS2. Because a lot of nodes access concurrently, so lock management becomes a critical component. And so this file system rely on a separate layer called Distribute Lock Manager, or DLM. To understand how DLM works, we should know two important roles in DLM, the owner node and the directory node. Owner node is that has an ownership of lock on a specific object. So simply, if you want to acquire lock, then you should go owner and ask request lock. But there's a question. Then how do we know that who is the owner of some file? And the answer is directory node, and directory node maintains the ownership mapping. So you should go directory node asking who is the owner of this file. Then directory node answers it. Then there's the same question. How do we identify that who is the directory node of that file? And the answer is they use the object hash value. For example, if hash value of object is 10 and the number of nodes is 3 in this example, then the directory node should be node 1 by modulo operation. This DLM is a fully distributed structure, so every node is a client. But at the same time, any node can act as owner or directory for some object. So let's see an example. In this example, node 2 is accessing file A, so requesting for lock for file A. And let's assume that node 3 is current owner, and node 1 is directory node for file A. First, node 2's file system requests lock for file A to its DLM. And DLM calculates the hash value and module operation, so identify directory node as node 1. So goes to node 1 asking who is the owner node of file A? Then directory node answers like node 3 is the owner. So node 2 goes to node 3, requests lock, and finally acquired. This is motivation. Look at this sentence. High contention means low performance. It seems obvious, but how about this sentence? Low contention means high performance. I don't think it's right, and this is the problem we found. Low contention does not guarantee high performance. What does it mean? Let's see this example. Node 1 is creating files and directories. If there is just only one node, then it shows this high performance as the right graph shows. But if we add idle nodes to the cluster, but still node 1 is creating file and node 2 is idle, so which means low contention scenario. But there is a performance degradation as a right graph says. And if there is more idle nodes, then more performance degradation. This happens especially in creation scenario, because in case of read and write, it is I/O intensive job, so the bottleneck is I/O. But this is metadata intensive job in creation, so the bottleneck shifts to DLM. Then let's see what happens in the creation scenario and check if there is something to optimize. But it's same as before. Request log for file B. Let's assume that creating file B. Request log for file B, identify directory, and query owner. The same as before. But in this case, file B is just created, so it means there was no owner mapping yet. Then, in this case, directory node simply assigned requesting node as new owner. So you can see this red owner mapping file B to the node 2. So directory reply, and node 2 becomes the owner of file B. So step 5 and 6, requesting to the owner and acquiring lock should be all done in the local node 2. So back to the scalability issue. Root cause was accessing remote directory node. Look at this example. If there is just only one node in the cluster, then every file's owner and every file's directory should be node 1 itself. So there is no probability to access remote directory node. But what about 2 clients? Then the percentage of remote directory node should be 50% because the hash of objects should distribute directory equally. And if there is 3 nodes, then it will be the 66% remote directory node. This is lock acquisition time distribution graph. And the left side, from 0 to 20 microsecond lock acquisition time means it is a local directory node. And the right side, remote directory node. And you can see that if there is more clients, and then there is a low portion of local directory node and more portion of remote directory node. If you see these 5 clients latency breakdown, there is a large portion of inter-node communication, which means have to access remote directory node in the DRM part. So let's review our motivation. There's 2 things. In the creation scenario, directory node simply assigns a requesting node as new owner. That was first. And next one is accessing remote directory node was the main overhead. So we suggest our new solution, Lockify, which means lock plus notify. And it consists of 3 components. And let's check this one by one. A self-owner notification is our key idea. We know that in the creation scenario, if we query the owner, then we know that we will be replied like, you are the owner, you are the new owner. We know that. Then how about, rather than querying owner, who is the owner? What about notifying owner that I will be the owner? Then what happens? We should not need to reply, wait for the reply, because we notified it. So hiding network latency, which was the big portion of internet communication. That was a simple but key idea. Next thing is extended lock acquisition interface, and which means shared disk file system should inform DRM that this is a creation, so that DRM should notify rather than query. Number 3 is asynchronous ownership management. Yes, we removed the reply, but we still send asynchronous acknowledgement to ensure consistency. For details, we maintain a wait list. So when we send the notify, then we add entries to the wait list. And when we remove it, when it is confirmed, then we remove it from wait list. And if there is no reply for a long time, then we retransmit it. So these are 3 components of Lockify. So before, the process looked like this. And now we enabled parallel execution. Evaluation. We implemented in the Linux kernel 6.6.23 on the top of kernel DRM. We also modified a file system slightly to use just a flags. This is testbed, and we connected to the shared storage through NVMe over TCP. Workloads. We used MD test as a micro benchmark, which create files and directories in burst. We both tested low contention scenario and high contention scenario. For the real-world workloads, we use Postmark and FileBench. About target systems, we tested GFS2 and OCFS2 as told before with existing DRM and our Lockify. We also tested NFS. NFS do not use DRM, but it is widely used for disk sharing, so we tested it for performance comparison target. How to see graph? This small red bar is NFS. These striped bars are existing DRM, and this is our Lockify, the colored bar. Since there is no reason to use a single client shared disk file system, you can consider this result as ideal performance. And you can check our performance gain in these 5 clients results. So in the micro benchmark with no contention, we achieved up to 6.4 times better performance. And this high contention scenario, yes, our approach started from no contention, but its benefit does not limited to no contention scenario. In the high contention scenario, which 5 clients create files and directories simultaneously in the same directory, we showed it achieved up to 5.4 times better performance. And for the real-world benchmarks, we use Postmark, which simulate email and web service. And showed up to 2.0 times better performance. And for FileBench, we use file server and web proxy, and up to 2.5 better performance. We also verified consistency using crash test, and Lockify scored the same level as DRM, so showing there is no negative impact on consistency. To summarize, we introduced new DRM by optimizing create operations, so hiding network latency. We achieved up to 6.4 higher throughput compared to the DRM. And thank you for listening.